G'day citizens, my name's Dave Finley. I will be your pilot today through this lecture and hope that you enjoy it. I've been in engineering over the past 50 odd years, not always in refrigeration. I started off in general engineering. This is where it all started when I was 16 back in 1973, so you can work out how old I really am. The Military Vehicle and Engineering Establishment. After I finished my apprenticeship, I moved over to the test laboratories where we used to do climatic testing on military vehicles, etc. As you can see here, as a military vehicle in for testing, we used to go from minus 40 centigrade to plus 50 centigrade with 60 mile an hour wind speed and could simulate solar radiation. The room itself was able to absorb 1.8 megawatt of wild heat, and this is where I got my love for refrigeration. I got to work for some of the major players in fridge, and was lucky enough to do some commissioning and sea trials on Type 23 frigates and also on Trident submarines. Engineering and refrigeration, I'm unashamed to say, became my mistress. I live and breathe it, and hopefully it'll do the same for you. Okay then, so off we go. A couple of statements first, just to start things rolling. Whereas the first law of thermodynamics states that energy can neither be created nor destroyed, only altered in form. The first statement of the second law of thermodynamics: heat flows spontaneously from a hot to a cold body. Now, that might seem a little bit obvious, but it's something you need to bear in mind. Well, what is refrigeration? Well, the simplest explanation that I can come up with is it is the process of moving heat from one place to another. For example, here, we have a fire at point A, and that will move to point B. And that is about the crux of it. It's all about moving heat from one place to another. So if we look here at a domestic refrigerator, where we have the freezer compartment, and then we have the fridge compartment, you can see the reverse side of the refrigerator. There's a heat exchanger on the back that we call the condenser, and the job of the condenser is to reject the heat from the food that's inside to the atmosphere in the kitchen. Okay, in this air conditioning example, where the heat is collected by the evaporator, in this instance on an indoor unit of an air conditioning system, the warm air goes into the unit and hopefully the cool air comes out. So that heat that has been absorbed is magically transferred to the outside unit and is rejected to atmosphere by the condenser or outdoor unit. Now here we have another example of an air conditioning unit where we have the inner unit where the heat is absorbed within the evaporator and that is transferred to the condensing unit where the heat gets rejected to atmosphere. Here we can see a basic water chiller. You have the process water inlet and the process water outlet, and we also have a cooling water inlet and a cooling water outlet. Now the heat from the process goes into the evaporator and is transferred to the condenser, which then goes out via the water to wherever we want to send it. In this case, it goes off to some cooling towers and the heat is rejected via steam. Here we have a water to air chiller. As you can see here, the heat is coming in on the chilled water from the process into the evaporator and hopefully out of the evaporator if the process is working properly. This has an air-cooled condenser where the cool air goes onto the condenser and is drawn through by the fans, and the heat from the process is eventually distributed to atmosphere. So in each of these examples you can see that the heat is extracted from a source, then transferred to another place where it's generally rejected, or it can be used in another process such as heating. Now the clever bit is that depending on how efficient the system is, and this is measured by its COP or coefficient of performance, which in a normal chiller is usually around 3 to 1, for each unit of energy input you can move 3 units of energy, i.e. 1 kilowatt of energy input, 3 kilowatts of energy moved. Now, I know this sounds a little bit like perpetual motion, but you have to remember you are not creating energy. It already exists. We are just moving it around. I'm just going to touch on units of measure. Temperature and pressure. In refrigeration, it's a minefield when it comes to units. But the most common units for industrial refrigeration are pressure in bar, temperature in degrees C, and these are the units that I will use. Temperature. The favoured temperature units are centigrade, Fahrenheit and Kelvin. Celsius, also known as centigrade in some countries, is a temperature scale that's named after the Swedish astronomer Anders Celsius. Now the freezing point of water is 0 C and the boiling point of water is 100 degrees C, and this is at standard atmospheric pressure. The Kelvin, symbol K, is a unit increment of temperature. The Kelvin scale and the Kelvin are named after the British physicist and engineer William Thomson, who was the first Baron of Kelvin. Now 0 degrees Kelvin, or absolute zero, is minus 273.15 degrees C, or minus 459.67 degrees Fahrenheit. Now the Fahrenheit scale is a temperature named after the German physicist Daniel Gabriel Fahrenheit, who proposed it in 1724. It says that 0 degrees freezing point of seawater and 100 degrees F is the blood temperature of a human. Just a few moments on the availability of heat. We assume that below freezing of water there is no heat available, whereas in actual fact there's quite a lot of heat available. If you look here at the melting point of ice, which is 0 degrees C or 273.15 degrees Kelvin, there's quite a lot of available heat going all the way back down to absolute zero, which is 0 degrees K or minus 273 degrees centigrade. So we can see from this there is actually quite a lot of heat available for use in heat pumps, etc. And all we need to do is to work out how we can extract and use this heat. Moving on to pressure, we have the bar, which the word bar has its origin in Greek, meaning weight. Its official symbol is bar. The bar and the millibar were introduced by Sir Napier Floor in 1909 and internationally adopted in 1929. The Pascal is another unit which is named after Blaise Pascal, the eminent French mathematician, physicist and philosopher who was noted for his experiments with a barometer. The name Pascal was adopted for the SI unit of Newton per square metre back in 1971. So 100 kPa equals 1 bar. PSI is another unit, which stands for pounds per square inch. It was an imperial unit before the metric system. It's used quite a lot in America, and it's sometimes used in conjunction with the Fahrenheit symbol. Just to complicate things even more when we're talking about pressure, there are two ways of recording it. Bar A, which is bar absolute, and bar gauge, which is bar G. Now, air pressure is a force of air pushing down on the Earth. Air pressure due to the weather, also known as atmospheric pressure, whereas air pressure is a result of the Earth's gravity pulling on the atmosphere. Absolute gauges would read 1 bar at standard atmospheric conditions, whereas a gauge that reads 0 at standard atmospheric conditions is known as reading gauge. Now, an absolute gauge, if it was up in space, would read 0 because of the vacuum of space, whereas on Earth it would read 1. Why is this important to know? Well, because most of the measuring instruments measuring gauge and most of the reference tables are in absolute. I don't know either. So this is it. This is essential that you understand fully the next few slides. Now don't skip them, and if it doesn't make sense, persevere and ask. Now I'll be using water as an example, but it's the same for all refrigerant compounds that we use. So, as we've spoken before and said, that water boils at 100 degrees C, but it also boils at 212 degrees F and 373.2 degrees Kelvin at sea level. Now, why is that important? Well, it's important because we can manipulate at what temperature these changes take place by altering the pressure acting upon the water. So we can alter the phase changes like this. Most pressure cookers have a working pressure setting of 1 bar over the existing atmospheric pressure. At this pressure, relative to sea level atmospheric pressure, water boils at 125 degrees centigrade, whereas on the top of Mount Everest, where the air is very thin and the pressure of the air is low, then the water boils at about 65 degrees centigrade. Now we can put the water into a vacuum jar, and in that vacuum jar we can make the water boil at just about any temperature we want. This shows the boiling point of water at different pressures. So at 23.4 millibar, water boils at around 20 degrees centigrade. If we go down to 6.1 millibar, water boils at 0 degrees C. Okay, let's get down to the nitty gritty. Types of heat. Sensible heat. Any heat added to a substance that changes its temperature and not its state. So, at sea level, from 0 to 100 degrees C, any heat gain is sensible heat. It does the sensible thing. It raises its temperature. As opposed to latent heat, whereas when the heat is added to a substance, it changes its state and not its temperature. So, water boils into steam or condenses from steam back to water. This is latent heat. Also, as ice melts and water freezes. Now, this is the holy grail of refrigeration. It's sensible heat and latent heat, because in refrigeration, it's the latent heat, the changing of the substance of its state, that does all the work. Now, let's take a look at the phase changes of water. There are three states. There's solid, which we know as ice, there's liquid, and there's gas, which we know as steam. Now, the triple point of water is 0.01. Now, the triple point is the point that water can exist in all three of these states It's not just water. You'll come across this if you ever get into work with CO2. Water is a refrigerant itself. It's known as R718, and we can manipulate at what temperature these changes occur. Okay, let's take a look at what happens when we start adding heat to water. Here we go with the temperature going upwards, and this way we got the addition of energy to the water. So we start here at around minus 10 degrees centigrade, and the temperature of the ice starts warming up. It's not changing its state at all because it's still solid, so therefore we've got sensible heat. It gets to this point here at 0 degrees C when the ice starts to melt. Now that ice is melting, melting, melting until it gets to the point where there's no ice left and it's only water, and that has all been latent heat. Then we start to climb the temperature again, and the water goes up and up and up until it gets to 100 degrees C. Now it's only changed its temperature, hasn't changed its state, so therefore again it's sensible heat. Then we get to the point where it boils, and the water boils away and boils away and boils away until we get to this point here where there's no water left, and we turn it from water to steam, and now the steam is warming up, and again it's sensible heat. Now just notice how much more latent heat we've had to put in than sensible heat to do the work. Now, there's two things that you should really remember. Refrigerants have a fixed pressure temperature relationship. This is known as temperature saturated, or TSAT, and it's the latent heat in a system that does the work. The changing of state from a liquid to a gas, or from a gas to a liquid. Now, the same thing will happen to all compounds we use as refrigerants, but at different pressures and different temperature relationships. Now, the next lesson, we're going to try and demystify superheat and subcooling. I hope you enjoyed it so far, and I'll speak to you soon.